operations.
Well, I did two things. When I first went out to PSL, we did what's called data reduction. And we had two different kinds of machines. I remember one of them was called Boresight, and the other one was called, I think, Ascania. Those names may be wrong, but when we first started out, and back in those days, computers were run with punch cards. So you put a tape of a missile chute on the machine, and the tape would go through the machine, and you would make certain measurements with the machine. In one machine we had two dials, and you were measuring the distance between 2 points. And so as that piece of film advanced on each frame, we would measure the distance. It would punch a card. And then those cards were accumulated and put into the computer for analysis. Then the Boresight machine was kind of a flat white table, and it had crosswires. It had two gadgets. You operated them, and you would get the crosshairs to go right over the missile. As the film advanced, you were tracking the missile with this crosshair as it moved across the horizon, and that's how they tracked missiles in those days. I'm sure it's much more sophisticated than that now. And I learned to hate the theme song for Johnny Carson, because my wife would wake me up. When Johnny Carson came on TV, it was time to wake old Gary up and send him out to the graveyard shift. I used to hate the theme song for Johnny Carson because that's when I had to wake up and go to work on the shift. But the beauty of that was I was able to work 40 hours a week. I was able to work 40 hours a week, take 18 credits, was married and had a baby daughter at that time. And that's the only way I could afford all those luxuries.
The cooperative programs got a further boost in the early 60s after PSL received a contract in 1958 to establish and operate a worldwide network of Doppler tracking stations for the Navy's navigational satellite system. As the satellite rises over the horizon, Station A receives a signal. As the satellite crosses the sky, Station A observes the frequency of the signal to change as depicted in Figure 1. The way in which the frequency changes provides enough information to determine latitude and longitude or position on the Earth of Station A. Likewise, Stations B, C, and D observe frequency signal changes as the satellite crosses the sky over their positions. Each station observes a different frequency shift since the stations are all at different locations. The graph in the lower left-hand corner depicts how the signal frequency varies for each station.
Typically, you may get a satellite pass every hour and a half. Back in the early days, when so much of the equipment was primitive, you know, then we had to have two trackers. When a satellite came over, there would be two students sitting with headphones on and actually lock on, what's called lock onto the signal, acquire the satellite. The data was punched out on paper tape at that time, teletype type tape. Then that tape there had to be a header. After the satellite had passed, there had to be a header attached to that tape which identified what satellite it was, what station. So a header was prepared and put on the tape, and then this was submitted via teletype back to a central processing facility which took that data off that tape and processed it. Well, again, the benefits to me personally was the added money. With a family, even though I had the GI bill, still with a family, it cost you money to go to school. So I got that benefit. Secondly, the second benefit is a break from the school. You just get tired of going to school after a while. Third, you go to work and you learn, you see the application of what you're learning in school, and that's very important.
Well, primarily we were looking for engineering students, and in particular electrical engineering, since that's the type of work we were involved in. But we had quite a few mechanical engineering students, civil engineering, chemical engineering. We also took people majoring in computer science, mathematics, physics, and a few other disciplines, but the majority of them were engineering students. We gave them 2 semesters of training here at PSL. The first semester after they were admitted to the program would be in basic lab type work, basic electronics, soldering, repairing equipment, and this sort of thing. And then the second semester, they would actually go into the tracking station that we had here at the lab and track satellites. Let me just say that throughout the whole program, there were over 1,000 students employed in the co-op program. In fact, I think the actual number that we have been able to account for was 1,005. We might have missed a few because we didn't keep very good records early in the program. But up until early 70s, we were really labor intensive. We would have 2 or 3 staff people out at a tracking station and have as many as 5 to 7 co-op students. So probably the peak in any one year would have been, well, let's see, probably 50 to 60 co-op students actually out in the field working at any one time.
PSL's data reduction contract ended in 1986, and the satellite tracking program ended in 1993. These two programs accounted for the largest portion of the more than 16,000 students employed by the laboratory to date. During PSL's early years, the laboratory established itself as a leader in one other business area that still exists today, electromagnetics. To complement its work providing telemetry systems, PSL also began developing the antennas used to broadcast and receive the telemetry signals. PSL formed an antenna section in 1950, and today, 46 years later, developing antennas is still an important element of PSL's overall support.
But the need for the antenna range grew from the need to make antenna pattern measurements particularly for white sands and military and experimental rockets and airplanes, particularly rockets at that time, that sounding rockets were coming in, and we needed antennas for links on that, and command destruct and telemetry and so on. The antenna range is actually a measurement facility at which or on which we can mount an antenna to be tested and some form of an illuminator to generate a wave that we use for testing. Then we move the test antenna to basically all angles, or at least all interesting angles, and measure the power radiated, the power density, and as a function of angle. And the result we call a pattern. It's some parameter, amplitude or power density or phase or polarization or whatever parameter of that radiating system as a function of angle is called a pattern. And we make antenna pattern measurements and other type measurements as well. Our range is unique and special in one respect. We have a lot of outdoor territory that most ranges cannot muster. And that makes a difference to those of us in the measurement community, because the need for elevated far-field ranges to be distinct from what's more modern coming into being due to lack of territory is the indoor or compact ranges, where they fold the range into a small chamber. Some of the small chambers aren't all that small, but still they're not the elevated far-field ranges that are many times needed. And we have a facility that very few can duplicate, and we can have ranges of many range lengths, up to 3,000 feet in our case. And the CSAT scatterometer antenna was in fact calibrated here on 2 occasions on our 3,000-foot auxiliary range at the mountain site.
Starting in 1946 with a few full-time employees and a handful of students, by 1970 PSL had grown to become a large and experienced provider of high-quality launch services and engineering development. Built around core capabilities in telemetry and data processing, the laboratory was poised to expand into new related business areas.